Hello Earthlings, imagine a cosmic object that spits out everything, light, matter, maybe even the secrets of the universe, kind of like the secrets you're hiding from your parents. Sounds like science fiction. Well, meet the white hole. Today, we'll see how it works, why scientists are obsessed with it, and why it's one of the strangest ideas in the universe. Buckle up, it's going to get wild. Alright, before we talk about white holes, we need to rewind a little. First, black holes. You've probably heard of them, those cosmic monsters that swallow everything, light, matter, even your hopes of passing math class. Once something crosses the event horizon, it's gone. No escape. Now, how do we know black holes even exist? Enter Einstein's field equations, basically, the universe's instruction manual for how space and time should behave around mass and energy. One of the solutions to those equations describes a black hole, a region of space where gravity is so intense, nothing can escape. And here's where it gets fun. Some genius physicists looked at these same equations and thought, wait, what if we just run this backwards? Boom. Suddenly, you don't have a cosmic vacuum cleaner, you have the exact opposite, a cosmic leaf blower. Instead of sucking things in, it spits them out. Basically, the universe invented a garbage disposal that throws trash back at you. To make this clearer, let's take a simple example, the number 9. You can write it as 3 times 3, but you can also write it as -3 times -3. Both are perfectly valid solutions. Similarly, Einstein's field equations have not one, but 2 mathematically authentic solutions. One of these solutions describes a black hole, while the other is most likely the solution for a white hole. Now let's differentiate between these two brothers. Black holes are cosmic vacuum cleaners, anything crossing the event horizon is trapped. White holes are cosmic fountains, matter and energy come out, nothing goes in. For stability, black holes extremely stable over time, while white holes highly unstable, even a little matter could disrupt them. And if we talk about interaction with surroundings, black holes capture and influence nearby matter and light, forming accretion disks and sometimes powerful jets. White holes eject matter but don't form long-term gravitational structures, making them less interactive. There's a common misconception about white holes. Some people think they repel everything that comes near them. But here's the thing, for a white hole to actually push things away, it would need to have negative mass. And, well, mass can't be negative. Just like black holes, white holes have positive mass, so they do attract objects. The only difference, nothing can cross a white hole's event horizon. Why? Because the event horizon is like an invisible one-way gate, matter and energy can only leave, never enter. It's the universe's ultimate cosmic bouncer, and you definitely don't get in without an invitation. Now let's move towards the formation of white holes. We will discuss about 2 theories. But first, it's necessary to know about the formation of black holes. So, how do black holes even form? Simple. Take a massive star, way bigger than our sun. One day, it runs out of fuel, no gas, no energy, no life. Gravity wins the fight, the star collapses in on itself, and boom, all that mass gets squeezed into a ridiculously tiny point. Spacetime bends, light can't escape, and congrats, you've just unlocked the universe's ultimate vacuum cleaner, the black hole. Alright, time for white holes. First up is the entropy theory. But before we dive into white holes, let's understand what entropy actually is. In simple terms, entropy is a measure of the randomness or disorder in a system. Picture your classroom with and without a teacher. That's entropy in action. Now, here comes some physics. According to the second law of thermodynamics, the entropy of the entire universe as an isolated system always increases with time. Imagine ice cubes. They automatically melt to water as ice have low entropy, and with time entropy increases and ice turns to water. But the same water cannot turn back to ice by itself as entropy won't decrease with time. So how are scientists connecting this to a white hole? Did they want to violate the second law of thermodynamics? Why am I saying this? Well, for a white hole to exist, entropy would have to go backward in time, which, as we know, simply cannot happen. Think of an ice cube. It melts into water over time, but that same water doesn't automatically turn back into ice. That's the challenge entropy poses for the existence of white holes. And here comes concept of local entropy. Now, we know our universe is enormous, seriously, as big as your never-ending to-do list after exams, but within this vastness, there are tiny regions that behave a little differently. These regions have something called local entropy. Under very special conditions, local entropy can actually decrease for just a fraction of a second, without breaking the second law of thermodynamics. And it's during these fleeting moments that a white hole might form. Once it forms, it ejects its matter out, and then, it immediately collapses. This theory also explains why white holes are so unstable. As soon as they do their cosmic, spit out, act, poof, they vanish. And maybe, that's why we've never actually observed one in real life. Now, let's talk about the cosmic bounce theory, and trust me, it's way cooler than it sounds. First, a massive star collapses under its own gravity and forms a black hole. Inside this black hole, gravity becomes so extreme that matter gets squeezed and squeezed until it reaches something insanely tiny and dense, what scientists call a Planck star. Think of it like the ultimate cosmic stress ball, compressed to the smallest possible scale. But here's the twist: quantum physics doesn't like infinite squeezes. At some point, quantum pressure kicks in and says, stop right there, gravity. And here's where the magic happens. After its fight with gravity, the Planck star bounces off the black hole. Instead of being crushed to nothingness, it rebounds. And that rebound, boom, it could explode outward, releasing everything it swallowed, but in reverse. That's what we call a white hole. Basically, the black hole eats, compresses, and then, spits it all back out like the universe's own recycling machine. Now, remember when I explained entropy, the measure of disorder in a system? Normally, entropy always increases, and a black hole seems like the ultimate symbol of that. But local entropy fluctuation theory says that in rare cases, entropy can actually decrease for a moment in small regions of the universe. That's exactly what this bounce looks like, a rare reversal of disorder, where the Planck star resists collapse and flips the script. So, in a way, the cosmic bounce theory and local entropy theory shake hands, showing how even the universe's messiest eater might one day spit things back out. And now, something real to blow your mind. In 2006, NASA spotted a gamma-ray burst that lasted for about 102 seconds, that's almost 2 minutes of pure cosmic fireworks. Now, what was so special about this burst? Well, usually gamma-ray bursts in space last only about 10 to 12 seconds. But this one, it went on for nearly 10 times longer than normal. And that's what makes it so extraordinary. Some scientists even think this could possibly have been a sighting of a white hole. Maybe the universe just loves to show off sometimes. Either way, it remains a cosmic mystery waiting to be solved.